our 95% confidence interval example was what we call the two-sided example, because we had 95% in the middle and then we had 2.5% out in the tails on either side. Sometimes, though, we're not interested in sort of the central kind of thing, and rather we're interested in some sort of extreme value, and whether that's upper or lower bound estimate just depends on the particular application. So in that case, though, we are looking at what we call one-sided, and so it helps to talk a little bit about the symbols here that we use and commonly in the tables. When it's a two-sided, we're talking about this as alpha over 2, and that's because this 95% is the 1 minus alpha percent level. So alpha gets divided amongst two tables, or two tails, that is. Whereas in the one-sided, then our alpha would just be there associated with the one table. So you have to be very careful in thinking about what it means, whether you're doing two-sided or one-sided. It's an easy way to make a mistake. For instance, here for the one-sided 95% confidence interval for the true mean, we're going to go look at that cumulative value off the standard normal table associated now with 0.95, not 975 like we would do in this other one, and that would give us a U value equal to 1.64. Right? And that would, in this particular case, if we work that all out, say for the lower bound on that, we'd have x bar minus 1.64 sigma x over the square root of n, and that would be equal to 18.55 in this case. Right, so the key thing being that this U value is going to change for the same amount of confidence if you're one-sided versus two-sided. So that's one critical area. The next part that I want to address is the meaning of confidence, because now we have a very tempting numerical measure of confidence, and yet it can oftentimes be misinterpreted about what it means. And so this confidence level, 95% confidence level, is about the process used to construct the interval. Right? This is, again, a difference between looking at a sort of prediction as opposed to looking at what happens after the sampling has happened. And then also a critical part of the meaning of confidence is that we can turn this into a frequency kind of statement, but we need to be thinking about repeated random sampling and then the associated frequency related to the construction or constructed interval. Right? It might help to take a look at a figure here in your textbook. So here's figure 8.1 of your text. And note that what they've got here are confidence intervals that are associated with random sampling. And that means that, for instance, in our example, we were doing a whole data set of n equals 19, or sorry, n equals 16. And if we were, and then we constructed a confidence interval. If we then redid the random sampling, redid the tests, so a new set of data from the same population and then construct an interval. Here's maybe the new one. Sample mean will be different, of course. And we repeatedly do that. Right? And we've got 16 of them shown here. Then it is true to say that if each and every one of these is a 95% confidence interval, then 95% of these confidence intervals, would contain the true mean. On average, in the long term, 95% of them would contain it. That's not the same thing as saying there's a 95% chance that the true mean is in this interval. It either is or it isn't. That's an incorrect statement to say that there's a 95% chance that that true mean is in the interval. That's not what this 95% means. It only means that if we construct the interval in this technique, then in the long run of repeatedly creating intervals, we would end up with 95% of them in the long run would contain the true mean. That's a goofy kind of statement that's a little different than what we're tempted to do to think, and it leads one to thinking, well, A, what's the real use of these things, and B, why not go with a higher level of confidence? What is that going to tell us? And that's what we'll demonstrate here shortly. So one of the uses of confidence intervals is in experimental design. Where we might want to specify the error in estimating our true mean. That error being equal to the difference between our sample mean and the true mean. I take the absolute value of that. Okay, so here again, turn to a figure in your text. Figure 8.2, and this probably comes out fairly lightly, so I'm going to draw back over this and highlight this a little bit for you. There's our horizontal axis, and here's where x bar came out to be. There was the true mean, so there's your error between those two, and based upon our sample mean in data, we can construct the confidence interval for the true mean, in this particular case shown here and here. Just want to emphasize again how this is a two-sided one, so this notation of the z sub alpha over 2 is talking about half of that alpha value being out in the left-hand tail and half of that alpha value being out here in the right-hand tail. Right? So we're now going to specify what this error is allowed to be and ask the question of what is in the sample size for the specified confidence level. Because specifying the confidence level specifies the alpha over 2 of the tail values, and that tells us what the u value or z value should be. Right? And so really that estimate we've gotten, or the bound on the interval, can be solved for our sample size, and that's going to turn out to be z alpha over 2 times sigma over our error that's permitted, all squared. Okay, so note here that you're going to want to round up our n value, right, to create an integer, and that the length of the resulting confidence interval is going to be equal to 2 times the permissible error. Right, so your confidence interval was x bar plus or minus the error, and that part right here, that was the part that's associated with the z alpha over 2 sigma over the square root of n. Hence where we ended up with that that expression. Okay, just a couple little more points here, and that is that the higher the confidence level, means something that isn't actually particularly useful, because higher confidence means a larger interval, and that's why it's not going to be a particularly useful kind of thing. For instance, we were working with the 95% confidence level, and our u value is plus or minus 1.96, and we had an interval that went from 16.95 to 36.55. That was already a rather large interval to begin with. If we were to go up to the 99% confidence interval, u would equal plus or minus 2.58 off of the standard normal table, and that would give us an even larger interval. So it didn't really help us to have larger confidence. And indeed, if we went up to 100% confidence, well, wait a minute. The standard normal variable goes from minus infinity to plus infinity. And so to get 100% of the area means we'd have to go to that bound of plus or minus infinity. And so our interval would be plus or minus to infinity, and all we'd be saying is I have 100% confidence that the true mean is between negative infinity and plus infinity. Absolutely a great statement, and you could even say, turn this into, there's a 100% probability that the true mean is between minus infinity and plus infinity. Of course, it really means nothing, right? It doesn't help us at all. And so, wait a minute, how we go back to that same question I sort of posed before of what good are these things? Well, I go back again to, well, you can, in experimental design, with a certain permissible error, you can then determine what the sample size ought to be. Also note that the larger our sample size is, the larger n will reduce the corresponding interval size. Put more money into testing, and you'll get a smaller interval size, and therefore a higher level of confidence, everything else being equal, to the where the true mean is at. So let's go back to one of these. If I were to go up to, say, 99% confidence, and I ended up with, even with this large 2.58 u value here, which goes into this z alpha over 2, really. Well, if this interval turns out to be quite small and acceptably small, then I've got something. And that's sort of the perversity, in a way, of this whole thing, that if we end up, it's a big if, right? If we end up constructing the confidence interval and it turns out to be a real small, tight window, then we're cooking with gas, as they used to say, right? But if we construct it and it turns out to be a pretty large one, and this one is fairly large, then what do? We either go and we increase n, the sample size, or we may be in some ways stuck here, and that is that if the underlying variation that's happening is just simply large, then there's not going to be a lot we can do, other than, we can spend a lot of money on trying to increase the sample size, and that will have some benefit, but This is also partially being controlled, of course, by the underlying population variance. So that's kind of a key thing here, that yeah, you can drive down the variance on the sample mean by increasing n. Unfortunately, that's related to the square, or 1 over the square root of n, and so that's kind of a little bit of a challenge. Boy, you have to quadruple n in order to get a 1/2 factor later on, right? Because 1 over the square root of 4. The other thing is that whatever the underlying process variation is that's at work is going to really get you in this whole process as well. So those are several key factors that do limit how we interpret what these things mean, but they do allow us to come up with a way to quantify our level of confidence associated with the data that we've gathered. In this case, only focus so far on the sample mean. We're going to broaden that out into some other things here in just a moment, but first we'll still play around with and work with this mean as we begin to relax some of the assumptions that we've used thus far. One of the critical ones of which was that somehow we magically know what the population variance is.